Hopefully you've all got access to the Moodle site by now, signed up. Anybody not signed up?
I mean, I tried it last week, and you came in with a password to get us. You came in as a visitor, not as a student. So did it change?
It works now. It should be okay. Yeah.
Okay.
Okay, so for those of you on CSML, I asked to send me we need a course representative. I didn't get any response from you. We urgently need to do it. So I need now
Course representative.
Stand up to the task of being your CSML program representative. Be interested in carrying out this wonderful duty. CSML representative. Yeah, do it. Just remind me your name.
Thank you.
Thank you, wonderful. Okay, so this week I probably will announce the first assignment. Okay, so you will be done via Moodle. So you need to keep your eyes peeled on Moodle. I don't know exactly if Moodle will email you. I don't know exactly how that works, or but be alerted that it will be announced. Okay. Just to remind you again that this exercise I've done this week for Friday, and Chris will be taking over from me. So that will be the usual setup for Friday tutorial session. Okay, do you want to go over some of the solutions for the MATLAB solutions, or do you want me just to post them online, preferably? Which would you prefer? Post the MATLAB solutions online, or
Post them.
It's probably a little bit easier, I think.
Yeah.
So I think we will forgot exactly where we got to. I did this, right? We were working our way through this further example.
Slide 11.
Slide 11.
Wow.
The independent deep network part 1.
Oh, yes. Great, thank you. So the bigger picture is, what I've been trying to say is that, first of all, I've tried to infuse you with the idea that probability is kind of an interesting framework, and that graphical models, as we will see, is actually, in some sense, really a great framework for helping describe many things we do in science, actually, not just in machine learning, statistical areas, data analysis. Well, we have this problem, and namely that probability is very difficult to work with because for various reasons. One of them being that the burden of specification is extremely high. So if you want to specify a probability distribution over n variables, let's say they're binary variables, then you're going to typically need of the order of an exponential number of states to cover n states. So this is clearly not going to work. Yeah, so I don't quite understand this definition of things. Okay, so the key trick that we're going to use and exploit in all science, and in machine learning in particular, is the idea of independence assumptions. These will help reduce the burden of specification in terms of get around this exponential complexity of specification, and they will also help us to do inference in a tractable way. So this is why this is such an important thing. So what I'm first going to try to think about, just go through what we talked about last week, is this idea of conditional independence and marginal independence, and the semantics of how this works with belief networks, okay, to give you some intuition. So the first thing to remember is this graph I showed you last week, ABC. So we remember that all distributions have to be these directed acyclic graphs. So something like that. Actually, the first thing I want to maybe just address now, I might come on to this later a bit, is why do belief networks have to be directed acyclical graphs? Why do it have to be? Why do I say it has to be a diag? And the reason is it comes from Bayes' rule. So let's say you have three variables, say x1, x2, x3. So from Bayes' rule, we know we can write this to say x1 given x2 and x3, bx2, bx3, right? And this similarly can be written down here as p of x2 given x3, p of x3. So if you were to write this as a graph, you say x1, x2, x3 is a belief network. This would be x1 given x2 and x3. x2 given x3 times by p of x3. And I think it's fairly intuitive that if you were to say extend this to n variables, you could write the first one as p of x1 given x2 to xn times by p of x2 to xn, right? And you just recursively deconstruct this to say, well, this could self-order x2 given x3 to xn times by p x3 x4 to xn. And you keep going. This could self-order as x3 given x4. So you end up with this decomposition that any x so something j's bigger than others. You know what I mean. Okay, so the point about this is that if you write this, of course, then as a graph, what this means is that you've got an ordering of the variables x1, x2, x3, blah, 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 to xn. So the first one that we did simply said, well, x1, of course, then depends upon all of these guys, like that. You get this full connection. Similarly, x2 will depend on all its predecessors as well, so and x3, etc. So clearly, actually, what this means is that there's, if you've done it in this way, convenience advice, you can see there's a kind of a feed-forward structure in terms of the arrows. So what that means is that there's no way that if you start at any node here, because of this feed-forward nature of the arrows, you can ever loop back to another node in this graph, right? So by construction, this graph is a directed acyclical graph. Okay, so what this means is that if we use this belief network representation, for it to be a probability distribution, it must be a DAG. Otherwise, it doesn't make any sense. So that's why we are in this DAG world. Okay, so that's why when we talk about now independence, I have to make this. I'm going to think about three variables, and I'm going to try to figure out DAGs, which are going to be distributions because they have to be DAGs now. And so whatever DAGs I construct, I'm going to drop one link in order to make some conditional dependency statement. But whatever it is, it has to be a DAG still. So there are more graphs, if you like, with oriented edges, but not all of them are DAGs. So I'm only considering the DAGs, and I'm going to remove an edge in the DAGs, and I'm left with only 4 graphs. These are all the graphs which are DAGs with one edge removed. Okay, so Then what I'm interested in is which of these DAGs are the same in terms of the conditional independence assumptions that we are specifying. And so I will, you can use Bayes' rule, for example, on the first one. So there's A given C, B given C, and that's by P of C. So I'm interested in whether or not A is conditionally independent of B given C. If I just work through Bayes' rule and the definition of that particular DAG, I see that I get indeed the factorization that suggests, and tells me in fact that A and B are conditionally independent given C. Okay. And similarly, the same is true for B and C, even though the arrows are going the other way. Right? Somewhat different. So the important thing about that is that this is a little bit of an unfortunate situation, maybe in some ways, that those graphs, although they all look different, they're actually exactly the same, at least from the perspective that we have in the moment. Okay? There's no difference at all. This is kind of an unfortunate sort of situation that many graphs represent the same thing. It's not a one-to-one correspondence. Now, the other graph, though, the D, is not the same. This really is different. So if you look at this thing here, A and B given C, well, you've got a term PC given AB times by PA times by PB. Now, there's no way, unless there's something very, very special in here, but in general, there's no reason why this thing should factorize functionally as some function of A times by some function of B. There's no requirement for that. So you cannot say that this thing here will therefore imply conditional independence. It doesn't. So graphically, if you like, there's nothing to suggest that A and B are conditionally independent given C. Okay. So this is kind of an important thing, and the way to look at this is that these two arrows, they point inwards towards C. And this is called a collider situation. Okay, the two, some people call it a head-to-head, different phraseology as well. And that's the distinction. All the other interactions here at C are not collider interactions. They're not head-to-head interactions. They're not both pointing towards C. So this collider will play an important role in assessing whether or not variables are independent, conditionally independent. Now, marginal independence, you can take the same four graphs and ask a similar question now: are A and B independent? So, to assess that, we're going to have to sum over C, see whether or not then the marginal over PA and B actually factorizes into PA times by PB. Okay, so we could do that. So let's look at A to start with. So in A we have P of A given C, P of B given C, and P of C, and to get P of A and B, I'm going to have to sum this over the states of variable C. Right? That's the definition of that. And I'm interested in whether or not this thing then factorizes in a function of A times by a function of B. Well, it just doesn't. Right? I mean, if there's only one state of the variable C, it would do. Right? Because then we'd have some function of A times by some function of B. But in general, distributions have more than one state. So you're going to get a sum of products, which itself cannot necessarily be factorized into the product. There's no reason that that's not generally possible. So this itself here, in general, there's no general functions such that this could be always written as some function of A times by some function of B. It's just not generally possible. So again, in some sense, there's nothing graphically either in A, B, or C which would imply generally that A and B are independent. D again, though, is different. In this case here, we've got, this is our, again, our marginal thing. We plug in now the form of the distributions. We've got C given AB, PA, PB. And now, I claim this is true. I just want to spend a little bit of time on this, because sometimes people are a bit confused why this holds. Is it obvious why that holds? Pretty, I think it's clear. Is it clear? So most students, about a third of the students ask me the day before the exam, why is this true? So I imagine that it will be the same with you. Who doesn't understand why that's true? Yeah. Okay. So let's just go. Okay, so we've got the sum of the C, PA, PB, PC given A and B. Now, this thing here, these two things in fact, they don't depend on C. Right? So they're completely independent of C. So what that means is that you can rewrite this as PA, PB, sum over C of P of C given A and B. I mean, effectively, these terms are like constants. It's equivalent to saying something like, well, you know, I want to sum over something, some function of variable x is some constant times by f of x. That's clearly equal to some constant times by the sum over x and f of x. It's the same thing. And this is equal to 1 because it's a probability distribution. Whatever A and B are, whatever states they are in, it doesn't matter. We're assuming that we're working with probability, so this must be equal to 1. So that's why that holds, and we've got this factorization independence property. So marginally they're independent. Okay, so in fact it's the converse of the previous case. So marginally these A and B are independent, but conditionally they are dependent. So that's the opposite in some sense. Okay, so like I said, the key thing to see here is this collider aspect. So conditioning upon C actually makes the causes, if you like, A and B, coupled. You have to sort of know something about how these causes conspired in order to give rise to this object C. And this non-collider case here, effectively what's happening mathematically is that when you condition upon C, you are kind of cutting you got a C given A, you got a B given C term, and when you condition upon C, you're going to get a factorization term, and it will separate A from B. You're mathematically cutting that thing. So that's why they become independent. That's a non-collider situation. So one way to try to maybe a little bit more intuitively think about this is through this kind of connection graph structure. So let's look at this example here. Here's a graph. The question is whether or not A is independent of D given B and C. So what I'm doing here is the yellows will be in the conditioning set. And well, what is going on? Well, so you know, here if you're conditioning up on B, well, that's not going to induce independence between A and C in some sense. On the other hand, here you've got a non-collider, right? So what that's going to mean is if you condition on this collider, that's going to cut the path mathematically between D and A. So you're going to get this factorization. It's going to factor whatever is some function dependent on C and D here from whatever is above it in this graph. Do you see that? Maybe I just show you here. So you've got P of D given C. You've got P of B given A and C. P of B given A and P of A. And now I'm going to condition upon B and C. Okay, so what does that do? Well, we've got this is going to be a function of D here. So we're going to condition upon B, so that's going to be fixed, that's going to be fixed, that's going to be fixed. So whatever this thing is over here, this is all some function of A. For fixed C. There's nothing connecting now D with the rest of the graph. The conditioning on C. So even if I'd not actually conditioned upon on B, but just conditioned on C alone, this thing now is some function of A and B, right? So it's not a function of D. There's nothing, this is just totally factorized. The only thing which could have connected D to the remainder of the graph is this term B given C and A here. But by conditioning upon C, then this actually completely vanishes. There's no remaining conditional dependence on D. Yeah.
So what's the relationship between the directed and near directed graphs there?
I'm just trying to demonstrate that this conditioning upon C here kind of has the effect of cutting this link here in some sense. I mean, it's not a precise definition.
So it's not some precise type of graph on that side, it's just an illustrative.
Yeah, it's an illustrative thing. It's probably, we'll talk about a slightly more formal graph construction in a minute, but this is a kind of one way to think about it. It probably could be fully formalized as well. But the main thing to think about is this kind of idea that, you know, this, what you're trying to think about a little bit is that there's going to be, you know, if there's a path between two variables that you're interested in, A and D in this case, and if we're going to try to see whether or not there's a kind of connected path between these two variables, and if there will be, they will be dependent. If not, they will be independent. But certainly what will happen is if we, in the conditioning set, if that would cut a dependence, then that's the key thing we're going to be looking for. So let's look at,
Sorry.
Yeah.
Could I have one more question to the cover you? So I'm not quite sure about the third term. It's PB depending on A.
Yeah.
How were you able to come up to see straight away that this is the right probability for the graph? And I'm especially in regard, I mean, B depending on C is clear. B depending on A and C is also clear because both go into B. How did you come up with the third term? B depending on
From the, how do I get this term from here, from the graph?
Yeah.
Well, we've got, sorry, that's too long, isn't it? B given A, that's right, yeah. So, no, sorry, I'm screwing up here. It's B given A and C. We don't need that term.
The P of C is missing what?
That's better.
Okay.
Okay, so the one next to it. So is A independent of D, not conditional on anything. Well, in this case, actually, what's going to happen is that when we sum over B and C in this case to get the marginal, when we sum over B, this is the collider. So basically, what's going to happen is that that term will just go to 1. The term P of B given A and C, the B is only occurring in that term there. When we sum over B, this factor will just go to 1. So effectively, this link here, if you like, is being cut. So whatever's going to go on down here, we're never going to basically, we're going to isolate the dependence between A functionally and D. So this means that this will be some function of A times by some function of D. So they are marginally dependent. So similarly down here for this graph, what have we got? Well, so we want to know whether or not B and C are independent given A. Well, this one down here, when we sum over D, that's not going to do anything. That's just going to go to 1. So that's kind of like this path here, in some sense, won't do anything for us. We can kind of drop that. But this is a non-collider. So what's going to happen there is that that's also going to not cause any problems on the condition of on A. This case is still a bit different. This one here is going to disappear again. But this is a collider now. So this link here, this path will remain. So there's a dependency here. So even though there's no dependency here, there exists at least one path in which there is a connection, with which these two variables are connected. And if that's going to happen, then they will be dependent. Okay, so we'll attempt to formalize this a little bit more now. So this is kind of a slightly annoying kind of stuff, but here we are. So these are some general rules. We'll talk about another general rule later, which is perhaps a little bit easier to follow, but this is one of the standard definitions. So this comes from Perl. So you've got 3 sets of nodes, x, y, and c. And if also x, so c is going to be our set of variables, our conditioning variables, okay, to the yellow variables. So all paths from any element of x to any element of y are blocked by c. Then x and y are conditionally independent. Okay, so what does this blocking mean? So a path P is blocked by C if at least one of the following conditions holds. So there's a collider in the path such that neither the collider nor any of its descendants is in the conditioning set. Okay, so this, I mean, it sounds very, mysterious, but it's obvious actually, from what I said before, right? So if there is, if the collider is not on the path, if there's a collider which is not in the conditioning set, we're going to sum over that collision variable, which is not in the conditioning set. So if we have this situation here where there's a collider, what that will mean is we're just summing over that variable, and that variable will just disappear, it will just sum to 1. So that will cut that path. And the other slightly tricky thing we need is that we have a collider, but we could also have descendants, and I'll talk about that in a minute. If we have a descendant which is in the conditioning set, that will actually induce dependency, and this could, so we need to take that into consideration. Okay, similarly, if there is a non-collider in the path that is in the conditioning set, right, that will also break this path. So these are the 2 situations essentially we talked about before. So the path is blocked by C if either of these conditions holds. So that's so then what that means is then you have to check such paths from x and y and check whether or not you've got to make sure all of them will be blocked if you want conditional independence. Otherwise they are dependent. Okay. So we say actually graphically that x and y are deconnected if they are not all blocked. So if there is a connection, there's a path which is actually not blocked, then they are deconnected. And if they are not deconnected, they are deseparated. So this is a little bit weird. So so the thing is that if they are deseparated, so there's no connection path between these two variables, the two sets of variables, then they are necessarily independent mathematically. It has to follow that. And we'll talk though a little bit about So you might say, well, why don't we just use the phrase then independence instead of deconnection or deseparation? But actually, it's a little bit more subtle than this, unfortunately. So the point is that if they're deseparated, deseparation implies independence, but deconnection does not necessarily imply dependence in all graphs, which could be represented by the distributions, which could be represented by the graph. So maybe I'll give you an example of this. So say let's think about a trivial example. Here's a distribution. So A and B, what would it look like in terms of a diagram? It would look like this. So they are deseparated. There's nothing connecting these two variables. Any distribution you want necessarily then has this factorization structure. So they are always independent. Right? So this implies that A is independent of B. It's always true in any distribution which satisfies this structural property. Okay. But I could write down another distribution. We'll see an example of this later. Let's say so just somebody tells you this, and then they ask you whether or not if you condition upon C, say A and B are independent. Now, generally, you would say that's not true, right? Because if you condition upon C, there's nothing to suggest that this term here should factorize as a function of A and B. So what this means is that in this case, the graph, they're deconnected, these two variables, A and B. They're connected through this path. However, there could exist distributions for which you could set, say, C into some particular state, and for that particular state of C, actually it might well be that there's some C-specific factorization here. That's not possible. That would not violate the laws of probability. It's possible that there exists some distribution such that for some setting of the variable C, that this would actually somehow be independent. Indeed, I could choose a trivial one. I could say, okay, I will choose some function. Maybe I write it in a very complicated way and you cannot see it numerically, or it's such a garbage thing, that you cannot somehow see the wood for the trees. And in fact, it actually might be that C given A and B is equal to 1, right? It's just somehow independent. It's just that there exists a numerical specification of these tables, which actually renders this distribution independent of, but in this case, A and B, or possibly weaker, some factorization of A and B. It's not impossible, right? So what that means is that there could exist actually a distribution which is consistent with this bag structure, for which A would actually be independent of B, given C. It's possible. This is a trivial example. You might say, well, that's stupid. If you really knew that, you would have never written this bag in that way. But fair enough. But that's, if you're talking just in terms of structural things and what is and what isn't possible, it's possible. that's why we have this concept of a graphical sense of dependence or independence, in contradiction or contrast to an actual numerical or probabilistic sense of independence. So in this case here, there's no graph, there's no distribution which you could ever set which would not imply independence. In this case, there is a set of probability distribution which would actually render A and B conditionally independent. So deseparation necessarily implies independence, right? So this graphical independence, in some sense, actually really does imply probabilistic independence. But there exists, unfortunately, in this case, you would think, well, clearly, you know, a condition of C, A and B are necessarily going to be dependent. But that doesn't follow. There could exist a distribution for which that's not true. However, they're deconnected, but that doesn't mean that they are dependent necessarily. It doesn't follow. Deseparation implies independence, deconnection does not imply dependence. This is a slightly subtle thing. Do you get the point a little bit? Yeah, it's a little bit unfortunate, but these are basic, fundamental, important considerations in the representations of probability distributions when we think about graphs. So what is the meaning of this?
Very good, sir. Could you
Yeah.
discuss? When you talk about a path at the top, you're talking about a path in terms of the undirected links, in a sense.
It can be directed still. It's directed.
But in the collider case where you got
Yeah.
the A, B and C as the collider in the middle,
Yes.
you're saying you've got a path between A and B. in some, so it's in terms of you're not regarding the link direction
No.
in
no.
that sense for the
Yeah,
path.
so the graph remains directed, but a path is just a set of variables which are connected to each other, independent of the direction of the arrow.
Okay. And then when you talk about the connection graph
Yeah.
at the bottom, that's after breaking the links as described in the top.
Yes.
So that's what's left, the links to the left once you've taken out the blocks.
Yes,
That-
if you like, yeah.
One-
Yeah. So the way that people think about it more is that and this is a little bit complex, but in principle, what you're supposed to do according to this formulation here is you have to look at each of your variables, so A and B in this case, and let's say this is one variable in the conditioning set. You have to look at all paths which connect A to B through C,
Right.
and you have to check whether or not they're all blocked. So you have to do every one individually. So what I tend to do before was start to make a single graph. But I'll come back to there's another formulation which we'll see later on, which is a little bit simpler. But I just wanted to, the key thing I'm trying to think in part here, I personally never remember these rules. You unfortunately will have to remember them because this will be in your exam. But the intuitive thing is all to do with this collider effect. That's really all that you need to, in the depths of your understanding, really get. The rest is just some formal mathematical way to prove that your intuition is actually the correct thing. So what it means to me is I just look at all these things and I look at the paths between these two variables, and I see, well, if there's a collider on that path which is not in the conditioning set, well, that will just evaporate the path because it just something will be cut. If there's suddenly something which is a path and there's a variable there in the conditioning set, again I will just cut it. And I just look for all possible paths, and if one of them is not cut, then this means that I cannot say these variables are dependent. That's it. And the rest is just a horrible way of formalizing this mathematically. But maybe this thing, obviously, it's good to think about some examples, and maybe we can do some examples later today. Okay, so another thing that we can discuss is whether or not two graphs are Markov equivalent. What does that mean? well, what it means is that all of the graphs here, A, B, and C, are Markov equivalent. Just all it means is the set of independent statements is the same. Okay? So the A, B, C are Markov equivalent. And there exists a rule to figure out whether or not two graphs are Markov equivalent, whether or not they have the same independent statements. Okay? And the way this works is the following. You first form what's called the skeleton of the graph, so you just remove the direction of the arrow. So you form an undirected graph. Then also you look at the original graph again, and you form what they call these immorality sets. Okay? So you basically look for nodes A, B, and C, such that C is a child of both A and B, with A and B not directly connected. So, for example, this would be such a set, an immoral set here, because this is a child and the two parents are. Okay, I don't know if did you get this joke?
Yeah, we just got the joke.
Okay, so you do that, so you get these immorality sets. I think there's only one here, if I get it right. And then you form the skeleton, okay, from this, so you then drop the arrows. So you write down the skeleton, you write down the arrows. And then two graphs are Markov equivalent if the same skeleton holds for both graphs, and they have the same set of immoralities. So you need to do both of these things. So I've got an example here, and I just realised, of course, that I forgot what the answer is, but we can try to hopefully figure it out here. So I was going to go through this last week, and I realised I remember what the answer was last week, or figured it out, but we'll have to do it live. So what do you think about this situation? The question is, are these two graphs specifying the same set of independent statements? Are they Markov? So according to this rule, we have to do two things, right? We have to figure out the skeleton. Well, the skeleton clearly is the same. We drop the direction, the edges, the arrows, they're exactly the same. So we just need to worry about, in this case, the immoralities. So we need to write down the sets of the immoralities. So should we try to do that? What have we got for this one? So we said this, let's say, so C, D, E, where D is the child. That's an immorality for this one. I think that's it. I may or may not get this right, actually, so do help me. This is just got D, C, D, E. I think that's it.
C, D, E.
Wouldn't the first chart also the BDE one?
BDE. Yes, yeah, that's what's worrying me, because I was remembering from last week that actually these are not the same. So BDE. That's good. I think that's correct now. So the answer is they're not the same. Okay. So this is interesting. So in principle, what you have, and though you need to practice it a little bit more, is you have a very general rule for how to figure out what sets of variables are independent enough. we'll talk about another one later. And we talk about belief networks, which seem to be really, really nice. But there are limits. But the reason that there is this field of graphical models is that graphical models is not just about belief networks. And you'll see the reason I'm trying to explain here is that belief networks are only capable of representing certain kinds of independence statements. They cannot represent all of them, all dependence statements. So they are limited in what they can express. So if we look at this belief network here, just put this factorization, you can see that T1 is independent of T2 and Y2. So T1 is independent of T2 and Y2. So why is that? Well, look here, Y1, which is not in the conditioning set, is a collider. So what this means is that you're going to sum over Y1, right, to get the marginal. And when you sum over Y1, because it's a collider, this term will just disappear, and this link here will be cut, and this path, if you like, is blocked. Okay, so this means you're going to get a T1 factor, independent, whatever is going to go on down here. And by symmetry, this is also true just by switching 1 to 2. Now let's look at the marginal distribution here by summing over H. So, well, it's still true that in this distribution here, that in this marginal, well, that these two conditions above here are still going to hold. Right? It just, these conditions here don't depend upon H at all. So they're true also in the marginal graph, the marginal distribution. So the question then, though, is then how to represent the fact that we have these two independent statements in a graph which has only got now these 4 variables. And the question is, does there exist a belief network which could express these two conditional or these two marginal independent statements, which remains a DAG? Okay. And the answer is no, you cannot do it. There's no belief network in general which could represent both of these independent statements in the general case. So it's clearly true that we're going to have marginal independence here. So T1 is marginally independent of T2. That's clear, because if we sum over Y1 and Y2, these two terms disappear. So we must have a factor T1, T2. There's no way we can get around that. It must be in the DAG. So we cannot have direct links between T1 and Y2, or T2 and Y1. That cannot happen because that's not in this here, in the specification here. So the only two things that we're left with, you can have an arrow this way or an arrow that way. There's no other choice. So if you choose an arrow, say, going this way, so then we have a situation like that. Well, then you could sum over Y2, and you will end up with the fact that no, if you sum over Y1, we'll end up with T1 being dependent upon T2 and Y2, because this path then is no longer blocked. So summing over Y1, because it's not a collider, will connect all these variables, this path here, and we won't get independence. And the same holds this way around. In this case here, by summing over Y2, the remaining variables are connected together. That path is not blocked. So neither of these two can express both of these two things. It's not possible within a belief network to represent that. Okay, so this is a little bit, it's a limitation of belief networks. So they sound great, but you can't do everything that you can. So you might want to do with them more. So in some sense, probability is it's a richer thing than these graphs can, or certainly in this case, the belief networks can represent. And I believe it's a general situation that there will be things in probability which no graphical representation could ever represent. Now, it's not possible to ever represent everything you could want to do algebraically probability with a graph. So in some sense, algebra is more powerful than no unique way to do that. And that's why there are actually a whole zoo of graphical models and belief networks, just one animal in that zoo. It may be the most useful for our purposes, but there are many others. And we'll talk actually in this course about mainly two kinds of graphical models. Okay, so maybe I just wanted to, before we move on, explain a little bit about this collider situation and descendant. So we said that, let's imagine we have this situation now, and the question is A independent of B? So C is a collider, it's not in the condition set. When we sum over C, this time we'll just vanish to 1. Clearly A and B are independent, that's it. Now something which was not well appreciated in the literature apparently is this situation when you have this now D, which is a descendant of C. Now actually C is still a collider, but we've got this D term down here. And actually, if we condition upon D, what's going to happen is in some intuitive sense, because you know what D is, even though you don't know the state of C, we're going to marginalize over it, you know something a little bit about the state of C. Because if you know the state of D, you get some information about what C could be, what states of C could be giving rise to the observed state of D. So you get some information about C, it's not completely unknown to you anymore. So in some sense, this is like knowing something about C, which means that you know something about the causes A and B, which could conspire to constrain the likely states of C. So this is coupling actually again A and B. I mean, mathematically we could write that down. We say, well, P of D given C, P of C given A and B. And we're going to sum now over C, and D is going to be specified. So before, we didn't have that term D given C, so when we summed over C, that vanished to 1, right? And we got this independence. But now, though, D is fixed, but this means that this thing now, there's no reason when we sum over C that this will actually sum to 1. So we cannot say it vanishes for sure. So that's the reason for that additional addition in the path situation. Another thing to say is that this idea of a collider is a path-specific quantity. So C is a collider along the path A to B. It is not a collider along the path A to D. So colliders are properties of paths, not graphs. As such. So C may or may not be a collider, it's a path-specific issue. So you need to be cautious of that. So you just need to check all paths. You know, if the C is a collider on that path, etc. And verify those conditions.
Sorry, was the result the last one that they are not?
Yeah. So in this case, they are not. A is not independent of B. Given D.
Also, just why is C not a collider on the path from A to D?
Because it's not head-to-head. So when you're going along this path here, and you look at the sort of like the structure of that thing, it doesn't look a head-to-head collision. Okay, so this is all rather obtuse maybe, but it's kind of vaguely interesting. Okay, this is a little bit switching the topic now, but I just want to briefly touch on this. It's kind of an interesting but confusing thing. So once we're at this level of things. Let's think a little bit about causality. So somehow, graphs are about dependencies and independencies and correlation and all kind of things like that. Actually, there's really nothing about causation as such. So if I write down something like this is a little bit tricky because what does it mean? Does it mean that A is causing B? Well, it can't be really, right? Because in some sense we're just talking about probabilities, which in fact we know that this is actually completely equivalent to this. These two graphs are Markov equivalent. They are exactly the same thing. So it's kind of a little bit strange to think that A is causing B because, well, I might as well write the graph the other way around and which doesn't change anything. That suggests that B is causing A, so it's kind of a weird thing. But conceptually, people tend to think about things in a causal sense. But sometimes people use the term causal graphs a little bit, badly. But when we did that burglar alarm scenario, we also thought a little bit causally. Intuitively, you tend to think about things in a causal way. So the way that you would typically write down the model is you try to think about the root causes of things. They will be the variables, perhaps which are independent at the top of your graph, which don't have any parents, and then kind of the effects of children of these parental causes. That's the kind of intuitive way we tend to think about constructing these graphs. But actually there's nothing really in the mathematics which is saying A happened before B, therefore in some sense temporally caused it. It's not a causation thing as such. Right? So this is a little bit of the tension in this kind of area. Right? We're talking about things in a causal sense a little bit, but actually mathematically we don't really mean causation. And here's a kind of a pitfall that people can drop into. So we're going to look at this table here. It's about drugs. So we've got a bunch of people, some males and females. So the males were given this drug. 18 recovered and 12 didn't recover. So their recovery rate is 60%. It's quite okay. 60% of these guys basically recovered given the drug. Those who were not given the drug, similarly, put some numbers, actually 70% of them recovered. So it seems that for the males actually, it's actually in fact better not to give the drug because more of them recover. There's a higher recovery rate. Similarly for the females, some were given a drug, we find that 20% recovered, some are not given a drug, and 30% recovered. So again, it's the same pattern. That for the females, it's actually better not to give the drug because the recovery rate is better. If you combine these two tables together, we find that 18 plus 2, 20 people who were given the drug recovered, and 20 people who were not given the drug recovered, so the recovery rate 50%. Similarly, 16 people recovered, 24 people didn't recover, so 40% of people. So what this means actually in the combined male-female group, actually it's better to give the drug because more of them recovered. So there you are. So you're working now for GlaxoSmithKline, and then your boss says, well, how was it? What should we do? Is it working or is it not working? And he said, well, it works for females. Well, it doesn't work for females, and it doesn't work for males, but it works abroad. It doesn't make any sense. Right? It's just like nonsense. This is called Simpson's paradox. And this was a big philosophical discussion many years ago. What the heck is going on here? And this happens actually. Of course, in reality, it maybe doesn't happen so often, but you have to, it's a cautionary tale in understanding probability, or beginning to interpret probability. And the tricky thing is that as humans, we are very primed to think about causality. We impose kind of interpretations on these data, these probabilities, which really are not there. They're not implied by the calculations that we are performing. So there's a kind of, we are doing something kind of a little bit intuitively incorrect in our thinking. So maybe we can think about this in terms of a belief framework. So we've got drug, whether or not you give the drug, whether or not the person recovers, and this is the gender, male or female. So I can represent things in this way. I'm not making any conditional independent statements, doing things this way, but it's useful to write it down this way because I just want to know whether or not the person recovers as a function as whether or not they're given the drug and whether or not they're a male or female. So I'd like to have this term P bar given D and G. And I'd also like to have this term D given G simply because I want to consider the possibility that the doctor might be giving the person the drug depending on whether or not this is a male or female. There might be some decision the doctor is taking there. So when we are writing this distribution down, I can write it down this way. Okay. And what's happening is that when you're doing this observational calculation, you're saying, well, do people recover or don't they recover, given the male or female? You're working with this graph. We didn't make any conditional independent statements. It's not that we said, tell me whether or not males or females what's the recovery rate, given that in there was some conditional independent statement. I didn't tell you anything like that. So what that means is that you're effectively working with this distribution. But what that means is that this distribution may imply there's some gender-specific delivery of the drug. It could happen. But actually, what you really are asking or want to know from a sort of clinical perspective is, well, if I just give the drug to this group of people, I want to know it's working. I don't want to say, well, I'm going to first of all choose whether or not it's male or female at random, and then whether or not it's a male, I might decide to give the drug, the D given G term there. Do I flip a coin with some probability I decide to give the drug? You're not going to do that. You're going to separate this. You've separated these two cohorts. And you're going to give the drug to these guys and you're not going to give the drug to those guys. There's no decision about whether or not to give the drug to this specific patient or not. You don't flip a coin, D sample from P of D given G. You're not doing that. So what this means is this is actually wrong. This is not it's not an evidential graph in some sense. But the one that you really want to think about is this one here. So my take on this is that what we're thinking about when we separate these two cohorts and we give the drug is we're intervening in this situation. We are changing actually the distribution as such. Okay, so what we're really doing is we are simply going to give the drug that's going to be fixed for some people, and there's going to be some male or female person here. The question is, then whether or not you recover given the drug and the gender, or maybe you don't want to know about the gender. You can marginalize over that. Whether or not the whole cohort combined actually is going to recover. So we really need to work with this new graph, a sort of modified graph. It has got this connection here cut. Okay, and if you do that, and you can also write this as what's the probability of recovery given the drug. Some people like to write this as a double bar because just to sort of differentiate it from the fact that we've done some kind of interventional thing. We've modified the original distribution. So we work with this and we get a new thing here. And if you now work through the numbers with this modified distribution, so you work out the margin, you work out this thing, you work out this marginal here, you work out this sum, you'll find that you get the probability of recovery given the drug is 0.4, the probability of the recovery given the no drug is 0.5. So what that means in this case is it's better not to give the drug, which is consistent with both individual cohorts, the group of males and the group of females. But here there's no inconsistency. Okay. This is a little bit tricky. People, I don't necessarily claim I have the world's greatest insight into this, but rest assured that people were talking, were debating this for many, many years. What is the meaning of this and how can it be? And it's been, people write books on this stuff. But my take on it is simply, it's a very simple thing that when you're doing this original calculation over here to get these numbers, you are using the full graph, the full distribution. But that's not the question that you really want to know. You want to know here, if I intervene in some sense. When I intervene, I'm not doing something in a kind of random sense anymore. I'm not going to be flipping a coin to decide, well, whether or not I'm going to give this drug to this specific individual, depending upon whether or not they are a male or a female. So this term here, D given G, should not be there. You don't do that. When you set up your experiment, your intervention, you are not anymore tossing a coin to decide whether or not to give this particular person the drug. You make that decision. So what that means is that you have to make sure, in probability, whatever graph or distribution you're using has to match the actual experiment that you're carrying out. And that's for me the moral of the Simpsons paradox. The whole confusion is just that. So then there are rules, you can go into the more detailed discussions about this. Well, what does it mean? Well, actually, what it means essentially is that what these guys will do, the kind of the so-called do calculus from Perl, means that essentially wherever you've got these variables that you're intervening on, in this case drug, you essentially have to remove all of the incoming connections, all of the parental connections to those variables throughout the graph, and then you won't be in trouble. So this is the topic of, you could still argue, is this causal because there was nothing before and after context here? But this is some way of thinking about causality in terms of effects. Yeah.
The 0.5s where you're calculating the probability of recovery with drugs and without drugs.
Yes.
Are those meant to be the sectors? Are those meant to be whether it's for a male or a female?
And this one here.
In both.
Well, this is over the whole group. So there's not condition upon whether it's male or female here. So we're summing marginally over gender. So we're just asking the question, if you said, in some sense, just for the whole bunch of people, if I didn't tell you these were males or females, what would you do? You just want to know.
But is each one of those terms part of that sum though?
Yes. So
the 0.7 times 0.5 and then the 0.3 times 0.5. Is that because you're summing? Is each one of those part of that sum?
Yes. So this term, I don't remember which way around, but this term here, there is male and female.
Yeah.
So for this might be the male calculation here. So this will be the 0.7 sort of probability of recovery or figure it out. So for males the recovery rate was 70%. So I guess there's a recovery given males that were not given the drug, right? And the probability of being a male was 50% because there are how many? There are 18 plus 12 is 40 males, and there are 210 plus 30 females, so plus 10 plus 40 females. So there is many males as females. The probability of male is 0.5. So we carry out the other ones as well. So we're using the table information here of the two specific tables. I'm not using this, if you like, information here. I'm not using this final one. I'm just using the first two tables here. Okay. Yeah. So probability is a little bit tricky in some sense, It's kind of awkward thing. Okay, so that's that bit. I want to move on to something else, actually quite soon, to more general graphical models. So what we could do now is, actually I want the next time to tell you about, the next set, about another way to assess independence, which will be which will be more general than the rule I gave you now. Okay, so that's why I wanted to not do too many examples of the previous setup. So we can do two things. We can either have a break now, or we can move on to the next material now. It's up to you. What would you prefer? Have a break now, or to carry on? Who wants to have a break now? Oh, crikey. It's less than half of you. Fair enough. Let's move on. Okay, so we're on more general graphical models.
Could you just go to the exercise?
Okay, so we've seen a little bit about belief networks. Okay, so they're quite nice. They're kind of causal in some sense. We're going to talk a little bit about well, maybe I should just say, yeah, so belief networks, these are used a lot as generative models of the world. So in science, physics, chemistry, we often see belief networks because they have this kind of generative kind of idea, and we know that they correspond to DAGs. Markov networks, in this case, they are a little bit different. We'll talk about them. These actually have their origins in spin class theory in physics. So these have been around for a long, long time, since the early 1900s. They're used a lot in image processing. That's the main area. Also language modeling as well. Conditional random fields, etc. Markov networks. Chain graphs are basically just a mixture, kind of a marriage between belief and Markov networks. Factor graphs, we'll talk about these. These are often used for computational analysis, and there are many other kinds of more advanced graphical models. Again, because there are many things which, none of these graphs is able to represent all of the things that algebraic probability can do. So that's why there are other things. So what is a Markov network? So a Markov network is defined as an undirected graph, and we've got cliques. So here's an undirected graph, and we've got some cliques. So what are the cliques? We've got a clique AC, CD, and BCE. These are the maximal cliques of this graph, this undirected graph. And the way this works then is the distribution is a product of non-negative functions on these cliques. Okay? So that's these psi's they're called potentials, and the potential is the same thing as a probability, except that there's no normalization constraint. So it's just a positive or non-negative object, usually positive. It's not zero. So these are so you have a clique potential, and you take the product of them, and this Z is just there to ensure overall normalization of the distribution itself. So in other words, the difference is that these terms here, we're not specifying local probability distributions. It's just that these local terms conspire to specify a joint distribution. But we don't say whether or not a particular sort of collection, subset of the variables in some sense is related to a distribution. It's not. Okay. And yeah, so this is a kind of example that you'll see in if you do vision lectures. Vision. Yeah. So let's say that you've got an image, okay, on a grid on the left. It's a two-dimensional image, and you have some corruption of this thing. Okay, so maybe some of the pixels are being flipped. Let's say the binary +1 or 0, 1 pixels, or -1 +1 in this case. And they're being flipped around with some probability. Okay, so you've got some kind of independent flip noise. Then we could write a graph that looks like this. So these are grey circles here. These are actual observed values that you have on your image. Okay, so it's a corrupted image. But do you believe in the concept of a cleaner underlying image, from which these observations are formed? And what you want to do is you want to try to figure out what is that clean image which gave rise to this corrupted image you've observed. You want to clean up the image, to reconstruct a cleaner image. So how is it possible to do that? And how in the heck can you get a cleaner image from a corrupted image? Well, of course we have to make some assumptions. And one way to do that is to say, well, clean images typically are smooth, or smoother than random noise. So if I gave you an image, right, then I corrupt it by flipping some of the pixels. Typically, it's not always true, but for most images, you can have blocks of continuous or not particularly rapidly changing pixel values. That's the way images tend to work. So if you see something like this, which is isolated, which is a different sign, you might say, well, that's kind of candidate for being honest. Right? So in some sense, it's a concept of smoothness of clean images. We want to say that pixels which are neighboring each other are more likely to have the same configuration, the same state, but not. So we want to bias solutions, clean images, such that neighboring pixels are in the same state. So that's the kind of distribution we want to specify. I want to specify the distribution. So if I were to call so here now, X is a set of all clean image pixels. So it would be, thousands of them. Y is a set of all observed, corrupted image pixels. So we have a generative model like this. We're going to have, given the clean, how does the corrupted one work? We can specify, say, well, that could just be that each pixel is just corrupted independently. We can write that down. But I need a prior then on clean images. So how do I specify? I'm specify distribution over clean images, just under the kind of general idea that things which have pixels which are in the same neighboring state are more likely than others. Okay, so what I could do is I could say, well, I'll specify P of X like this, that would have a term could be proportional to product over all links, all neighbors I and j. I'll use psi fx sin xj, or for example, I could specify that to be e to the power xi xj for some numerical value beta, which is positive. So what does this mean? It means that if beta is, say, +1, if this +1 and that's +1, I get +1, e to the 1, so I get e, right? If I get +1 minus 1, I get e to the -1, which is less than a half, right? So it's 2.7 versus something which is less than a half. So that's clearly, whatever that term is, that factor is going to be a bigger contribution, they give a higher probability individually, this product, than the term for which they're in different states. So what you can see is that when I take a product of all these things, while some of them may be in different states, overall it's clearly true that if I had a distribution which all of these x's are in the same configuration, they were all up or they're all down, that would be very, very high, exponentially higher than some in which, you know, some are all the random, you know, they're in random configurations. Okay, and then I'll have some overall normalization constant here, which would just account for this fact that I have to make this a distribution. Okay, so that's the idea. And there's no sense of kind of causality here, or it's just a kind of neighborhood sense. We just want things to be neighborly related. Right? That's why there's no sense of directionality in here. It doesn't make sense. So the way we could write this down is that, so this is our joint distribution now. So it's going to be proportional to, this is P of x, and we could have some term here which is P of y given x. So this could just specify the corruption flip probability independently. So for each pixel, you know, you could say, well, this term here, this could be related easily to an equivalency. It's just P of yi given x on x. Okay, so then when you've got this thing, what you want to do is you want to figure out from this distribution what is x given y. So what is the distribution of x given the observed corruption pixels y? And that's going to be, of course, equal to P of y given x, px over py. So you might say, what is the most likely clean image given this corrupted image? So you might want to find the maximum which image is going to be the most likely from this posterior distribution. And that's equivalent to this thing, py given x, x. Okay, that's from base rule. But clearly this denominator here is not a function of x. So it's equivalent to this case, okay? So this would be the map solution. The maximum a posteriori probability. A posteriori state. Okay. This is the posterior, and we want to find the most likely state. So we call it map state. So I'll show you a demo of this after the break. But this is the kind of situation that we have. So here on the left is a 1 written down, and this is the corrupted version here. And then to find the map state, it's given by this thing here. Okay. And the tricky thing actually is that I have to be a little bit careful how I say this, but in general, so this sounds really nice, right? You can do this kind of thing, but it's really hard. Computationally, it's very, very hard. So there exists a very smart algorithm which is able to do this actually exactly in polynomial time for this particular problem. But it's very, very complicated, and I didn't implement it here. It's something simpler. But in general, it will turn out that for working with these graphs, that this is it's a very hard, it's going to generally be exponentially hard to figure out something like the map state, something like that. So what you will do, if you do the computer vision course, you will be looking at a particular algorithm called Graphical, which will actually help you to solve this particular instance in a polynomial time. And if you want to know more about it, you can also read the final chapter of this book. I'll tell you about a much simpler algorithm after the break, and we'll see it running in action. Let's reconvene at
quarter to 1.
Quarter to 1.